Hello, everybody. Welcome. Glad you can all take some time out of your day to come and hang out with us as we speak to Eros Fani. It's his first time up on a Twitter space, so very exciting. There's a really interesting topic he's got for us today as well, a research paper that has been submitted and released recently called DUME, Dynamic Upcycling Mixture-of-Experts. We're going to hear all about what that means. Eros, welcome.
Hey, Xavier, thank you for inviting me. It's a pleasure for me for being here to talk about DUME and talk with all of you.
Fantastic. Thanks so much for coming along. How's everything there with the setup? Your microphone's working fine, obviously. Everything else going okay?
Yeah, everything okay, I would say. I think also, I don't know if people can hear us, but yeah, for me,
Absolutely.
everything is okay.
Absolutely. Yeah. I believe they can. They'd let us know. Excellent. Eros, it's your first time up here with us, so I'd love it if you could give a just a brief introduction of yourself, a little bit about what you do at Jensen and your history and how you got there.
Yeah. Hello everybody. I'm Eros Fani. I've joined Jensen in October last year, working right now on Mixer of Experts and routing mechanisms, and more in general in distributed and decentralized learning. Last year, I earned my PhD in Italy, Polytechnic of Turin. I was working most of my career before Jensen in federated learning, which is closely related to distributed and decentralized learning in general. It's kind of a more specific topic still related to distributed, where you also have the issue of privacy, where people don't want to disclose their private data to centralized server. In the case of federated learning, there is a server. In decentralized learning, you don't have a server, but still you need to coordinate all of these nodes to train a model to solve a final downstream task. So yeah, this is kind of my story in 2 minutes. So yeah, if you have any other question, please.
Fantastic. I know there was a couple of terms you used there that I know are going to come up as we go along a few times. Give us just a couple of lines on what a ministry of experts is. Sorry, a mixture of experts. When you're referring to it that way, and a little bit more on the federated learning side.
Sure. So for regarding the first question, so mixture of experts architecture are born to scale up large language models to even larger models. So the problem is like, suppose you want to train a large language model. All of us, I think like most of people know that these models are extremely large and expensive to train. And the problem is that if you don't want to, you want to continue scaling it up, increasing number of parameters. But the problem is that if you do it in a, I would say like in a very easy way, like just increasing the size of the model, the problem is that you keep increasing and increasing and increasing. So like the problem is like we need to find a way to scale these models up while not overwriting the knowledge that we've already learned. So like people in the literature came out with this idea that is mixture of experts layers, where you can have after the self-attention blocks in your transformer blocks in your large language model, you can keep separate smaller experts, and each expert is able to specialize on some specific subtask or some specific domain, which you don't really have any particular grasp on what is happening inside when you train this mixture of experts model from the beginning. So like if you want to train all your experts of your mixture of expert model all together, you don't really know what is going to happen inside them because of the mechanisms of backpropagation and training in general. But the point is that you are going to activate a subset of these experts. So you don't activate all the single experts in each mixture of experts layer at every time. And in this way, you are able to reduce the cost while maintaining reasonably good performance. And yeah, for the second question regarding federated learning, in federated learning, I mean, it's kind of related to Mixture-of-Experts actually. In federated learning, you have several clients that want to collaborate together to construct a model that is good for everybody. But these clients have their own local data, and this data belongs to different distributions. And this distribution may definitely be different distributions. So it's not an easy task to solve, because you want to have this model that is good for all the clients, not just for one or two clients, right? And the problem is that if you want to have only one model for everybody, that's good for everybody, without disclosing the data from the clients, you need to construct a protocol, an algorithm that is able to train this model in a distributed way, okay? But without sharing any kind of private information. So there are like several techniques to do this, but all of them suffer from various complicated issues that, I mean, we can go through if you want, but like some of them is, one is, for instance, like destructive interference that we also have in model merging, that is an alternative that you could have when you wanna just mix like a model that you have like several models that have been trained on different domains. Suppose that I don't know, like you have models trained on mathematics, physics, or I don't know, like history data. Okay, so let's say you want to have one model that is able to solve Python programs. Okay, you want to generate automatically with your LLM some Python code. Another model is able to solve mathematical problems. Suppose that you want to then mix all of them. Okay, at the end, if you just do, and I would say like a weighted average, that is like the most simple technique that you can imagine, you will end up having destructive interference, which means like, well, your original models have been trained on different tasks, which means that the loss landscapes were very different. So when you do the average, you're gonna end up optimizing neither of these tasks, right? And what happens is that your final model is not good at any of the original tasks. And this is, I would say, like a slightly different variation of the federated learning paradigm, where in federated learning you have several iterations, while in here, in model merging, what you do is just saying, oh, well, I already have these models, I want to merge them. The problem is how to do this, okay? How to do this effectively. And apparently, like in literature, there are like so many papers trying to do this, but all of them still suffer, I mean, with different degrees of severity, of course, but they still suffer from destructive interference and also catastrophic forgetting when you, for instance, want to add another expertise later on. If you want to add it, but you already have your merged model, it's not clear how you should integrate the knowledge from the new expert into the model that you already have constructed.
Right. So effectively what you were looking at, the question you were looking at was how to take models with individual domain knowledge, combine them, make them smaller, and without losing anything.
Exactly. So we took like a quite different approach that goes into the direction of model merging. That is not merging, it's merging, which means stands for Mixture-of-Experts merging. In practice, what yeah, it's like a weird word, but
MOERGING, is it?
It is like yeah, I didn't get the spelling though. Like it is MOE and then urging.
Fantastic.
So yeah, it's like that. And yeah, the idea is that you don't do the aggregation of the parameters in the naive way as you do in model merging. You just do that kind of aggregation for some of the layers, not for all the layers. You try to actually, it's not you try, you keep separate the most important parts of your model that are the MLP layers in your transformer architecture. So let's say like in your typical transformer architecture, you have a cascade of self-attention MLP, and so on for several times. Supposing that you have like 5 models like this, okay, and you want to merge them, you don't do the merging, you do the merging, which means that you do the same kind of merging that you would have done for like using a standard algorithm, but you do it only for the self-attention blocks and some other layers, like the embedding layers, for instance, and the others, while you keep separate the MLP blocks because they retain the most specific knowledge for the domains. The problem that we address, because like this model merging is not something that we invented, it was already in the literature, but the problem was that the previous works didn't have a routing mechanism that was like defined from scratch, in the sense that all of these works needed to train on additional, needed to do additional training iterations on this final Mixture-of-Expert model, just to correctly route the tokens through the experts. And we addressed specifically this problem. So it's like, okay, I don't know if I was able to explain it, but if you got the full picture of the setting, you don't need to train anything because you already have all your models. For some layers, you do, let's say, an average. For the other layers, the MLP layers, you keep them separate. The only problem is that you don't have a way to initialize the router. That is the part of it's just a linear layer, actually. It's a part of the model that tells you where you should forward each token to which expert, okay? Right. And we addressed this problem. So like we wanted to fix the merging technique, providing a training-free algorithm that is DUME, indeed, like the dynamic upcycling Mixture-of-Experts. We named it like this because it is upcycling in the sense that you can reuse in a clever way the experts that you have already trained. Right. And it is dynamic because I haven't already mentioned this, but you can add or remove experts at any time without losing knowledge. And this is actually very seamless. You can do this seamlessly because, for instance, just if you want to remove one expert, you are able to literally remove all the knowledge that this expert provided. If you want, you can also not remove it, at least in part. If you want, I can explain it better later. But if you need it, for instance, like let's say there is one expert that says like, okay, I want you to remove all the information you get from my data, and I want to perform full machine unlearning. So just please forget about me. Okay, so this is the question from one of the experts. And okay, well, with this method, you can do this for real. Like you remove the expert, you remove the contribution, and you downgrade, I would say, the router. And you can do this in the both direction. So you can also like upgrade the router. If you want to add a new expert, you can downgrade it if you want to remove it. And this doesn't affect in any way the knowledge that you have already gathered through with the other experts.
Fantastic. You mentioned that some of this or a good bit of the theory was already in literature. What was unique about the approach that you took and the result being DUME?
Yeah, so the point is like in the existing literature, if you wanted to perform model merging, you needed to do further training, which means that you need at the very least collect some data somewhere and do the training. And this is quite difficult to do for several reasons. Like, okay, so like the final goal, as I hope it was clear through my talk, is to have this final model that is able to solve different domains, right? So like it's good at physics, history, coding, mathematics, and whatever you want. Yep. The point is, if you need to do additional training, you need to have this data somewhere. So basically, you end up doing multitask training that is very difficult. Like there are so many other problems, like just to mention one, catastrophic forgetting, which means like, well, I've learned to solve all the mathematics problems in the world, and now I want to learn how to write essays, let's say, okay. I start training on writing essays. So I train my LLM to write the essays, and then all of a sudden I discovered that the model is not able anymore to solve mathematical problems. So this is the issue with catastrophic forgetting. So you don't want, I mean, there are some techniques able to do multitask learning, but this requires you to centralize some data, which is something that you would avoid probably to do, because if you can just keep like the data where it is, or like exploit the knowledge that you have already extracted without doing any additional training, is so much better. I think it's very clear that if you can just do some arithmetic operations to integrate these models into one model that is plug and play and is already easy to deploy, and you don't need to do anything else to train it, is so much better for so many reasons. So like this is our real contribution. So we fixed that one last issue remaining in model merging, that is how do I initialize the routers? So
Right.
with our technique, you can initialize, actually, like, of course, like also our technique comes from machine learning research. We have applied one mathematical tool, that is ridge regression. We applied it in just like using it as if it was a classification problem where the labels are the domains of the original prompts. I can go through the details if you want, but the point is that this technique allows you to construct this router in a almost optimal, with an almost optimal solution, in the sense of the regularized least square error. That is like, okay, I know that this is some technicism, but I mean, just to give you an idea, it allows you only via some mathematical operations to construct these routers, and you don't need to do anything more. So it's just matrix multiplications and computing the inverse of some matrices at the end, which is very cheap to do. And yeah, you end up having this model that actually addresses the original question, that is how do I effectively combine these expert models to have one unified model, no matter how it is. We choose to do model merging because we had the idea for this technique, but like the more abstract question was like, can I unify these models in an effective way that is cheap to do, and also that allows you to retain the performance that the original experts had in their own domains.
Absolutely. So it can only be a positive to bring models, experts, as you said, in their own areas in together and effectively make them one larger, coherent model, avoiding all of the training using the free training technique. Be saving a lot of resources, time, effort as well, I imagine.
Yeah, exactly. So the only thing that you need to ask to the nodes is just to extract a bunch of statistics. So like differently from like just doing training, you need to have a few labeled data. Where labeled means actually the label is just the domain, so it's very simple label. It's not like I don't know. I mean, it's very simple to say like this is a mathematical problem, right? So you just need to say, well, this is mathematics, this is code, okay? And if you have this and you have it for, let's say, like we also proved in the paper, like you only need, in some circumstances, you only need like only 80 prompts per domain. So say you have 80 math problems, 80 coding problems, and so on. You just need to ask the original experts to extract some statistics, just doing forward passes through the model. So you don't need to have any back propagation that you typically have in the training, which is actually the most costly part in a training loop. So here is why we excel, I would say, like in the this method is like costly. If we talk about costs, it's very cheap because like you don't need to do any trainings, just forward passes through the models. And if you extract these statistics, and then you can collect these statistics together, and you can share only aggregate versions of these statistics and aggregate them again. And afterwards, you are able to just solve some mathematical operations and construct your final routers. And in this way, like you have finished your all your operations to construct your final merged model. And yeah, so
that's
yeah,
that's quite fantastic. I just want to stop on that for a moment. Are you telling me there that the models that are part of the Mixture-of-Experts and into DUME, you're only taking a certain amount of prompts and certain amount of statistics, and they're able to actually extrapolate accurately the rest of the training of the information. Is that correct?
Yes, it's correct. And like, I want to also add one thing about this. So when I said like you need to extrapolate some statistics, and I specifically said aggregated statistics, which means that you are not even disclosing. I mean, one could think like, what are these statistics, right? These statistics are not disclosing anything regarding the original data. So in the case like you have, before we mentioned like federated learning, we didn't develop this for federated learning, but it's actually suitable also in a federated learning scenario, because like since you only have to share aggregated statistics, there are some work, one work specifically that I want to mention, secure aggregation, where I mean, the problem in federated learning is that if you share, for instance, feature maps, there are some adversarial attacks that may give you some information about the original data distribution. And you don't want to really disclose this distribution in federated learning. With secure aggregation, which works if you have aggregated values, and if and only if, I would say. So like you can use secure aggregation only in this case. You can construct a secure setting where you are immune to privacy attacks, right? So to attacks that can hinder your privacy. And in this, I mean, and this is why I was like underlining the fact that the statistics that are shared are aggregated, so you don't really have this issue. And I mean, you can do it in a distributed, decentralized, federated setting. Is really, I mean, the same thing. The algorithm is always the same. So no matter how is your practical setting constructed, right? So the only point is like you need to follow the algorithm, but you can deploy it in any circumstances.
That's a really important point, actually. Thank you for stopping on that one. So we can get the benefit of the larger amount of expertise, knowledge, data, but it still remains private through the secure aggregation.
Exactly. Yeah, I mean, that's not like the one. It's like one potential additional good point of this algorithm. Though, like, I wouldn't say like this is the main one, because like the reason why we deployed it is just to find a way to upcycle, as the title says, to upcycle the experts in a training-free way. So like this is, in our opinion, the most important contribution of this work. But of course, like if you are in particular scenarios where privacy matters, yeah, you have also this benefit.
Absolutely. No, the upcycling itself is just incredibly impressive, and the other pieces that you've managed to include alongside it, I think various different sectors, as you said, would be very interested in. What are the main uses, or what's the future of DUME that you can see? Where is this going to be used? What kind of applications would it have?
Well, this could be used like in so many different applications. Like, I mean, the easiest thing that I could imagine is like there are so many models uploaded on Hugging Face. You can't really know how to use. Like, suppose like you just want to like, it's always the same example, I know, but like you want to have like this model that is like a generalist model that is able to solve physics, history, coding, and so on. You find in Hugging Face some models that are good in physics, some models that are good in coding, but you don't find this generalist model that is the best one in all of them.
Right.
And yeah, this is the answer. So like you just download these models and you combine them using DUME. The only, like, I would say it's a future work. It's very interesting work. For now, DUME works with experts that have been trained using the same original architecture. So let's say I'm using a Gemma model. I need to use Gemma for all the experts. So I cannot use like another model because, like, of course, like this is a research work. We started simple. Like in the future, it's likely that maybe we are going to investigate also what happens if you wanna merge. So Mixture-of-Experts merging. You wanna merge the models having different architectures. Yeah, I would say this is a future work. The application is already there. So like you have your models that are experts. You wanna combine them in a way that is not affected by destructive interference. The model merging is a solution, but you don't want to do further training, so just use DUME.
Fantastic. You did mention that currently it only works on models using the same architecture. I assume that that would be a possibility in the future of different architecture being used. Where else do you think DUME and this area of research will go next? Where will it take you?
Yeah.
Get your imagination hat on.
Yeah, I think that like there is room for improvement, of course. Like yeah, okay. One possible way to improve it is like, okay, we are using a linear layer for routing, right? What about using something that's not linear? There are some works that show that you can actually use a variation of the ridge regression technique that is called kernel ridge regression, where you can like model some spaces that are higher spaces than the spaces that a linear model that is, I mean, a linear layer, the DUME router is able to model you. So like again, we go into some technicalities here, but
that's okay.
if you have your data, that is not linearly separable, you don't really have a way to solve the task, right? So if the DUME router task is to correctly route the tokens from mathematics to the mathematics expert, you don't have a way to do that with a linear router if the latent space is not linearly separable, which is also something difficult to understand, to be honest. Like, it's not very easy to understand this because we are talking about hyperdimensional objects. So it's not easy to imagine, it's not easy to understand in practice. But anyway, like there are some techniques in mathematics that allow you to just not to construct layers that looks like if they are linear layers, but they actually aren't linear layers because there is an hyperdimensional mapping before happening. So this is one direction. The other directions, I think, they are even more interesting than that. Because I mean, at the end of the day, we are talking about a router that is important, of course, but the knowledge is stored in the MLP expert. So one additional direction that I think is very interesting is what if like the single MLP experts have a different architecture. So I would start like from having different architectures in the original experts. I would start from just looking at the MLP because like, of course, you need to build your house one block at a time, right? You don't start from the most difficult part. You start adding one piece every time. So what I would say, like, what would happen if I have MLPs of different sizes that come from experts that have the same architecture, but maybe, let's say, like I'm using a Llama 3B model for one expert, and then I'm using a Llama 9B model for another expert. So they are basically the same model, but they have different number of parameters. So maybe this could be like the very first step to approach the future of this line of research. But of course, I could say like we are already working with a similar technique to a problem that is related or not like exactly the same problem, that is routing at inference time. So in that scenario, the question is, how would you use your expert models? So like, I don't want to combine these models. I want to just know which is the right model to use for every prompt.
Okay.
So like I have one prompt. This prompt is, I would say like, it is like misleading. So maybe there are words that reminds you of mathematics, some words, but are for biology. Okay. And but if you are a human, for you, it's very easy to say like, okay, this is, maybe you can say like, oh, well, it's talking about blood cells. So it is, of course, biology, even if there is the word, the question in the prompt. Okay.
Right.
But maybe it's not the same case for an LLM. Of course, like you don't really want to use an LLM to understand the correct LLM to which to forward the prompt, because you are basically doubling your costs, right? If you use an LLM to make decisions to which LLM to be forwarded, you should forward this prompt. You are increasing the cost so much, and you don't want to do that. So we are working on constructing a router that is on the very top of the model. So it's just like before the models. So you want to use this router to just say like, well, for this prompt, you should use this expert. For this other prompt, you should use this other expert. Okay. So yeah, this is, related, though like not exactly the same thing, because you will not end up having one single like multi-domain expert model. You will end up still having like these several experts,
Right.
but at least you will have a mechanism that will allow you to just select the best one every time.
Fantastic. I can't wait to see that one. That come through as well. Well, thank you very much,
Sure.
Eros. That was absolutely enjoyable. Sounds like you've got a lot of very interesting research ahead of you to get through to the end of everything you were imagining for the future there.
And thank you. Thank you also to all the attendees. It's been a pleasure as well to share my research with everybody.
Absolutely. Thank you, everybody, for coming along. We'll be scheduling some more of these for next week, and we'd love to see you all again. Thanks, everyone.
Thank you. Bye-bye.